Hello and welcome to session number 3. This is going to be a fun session with essentially no mathematics. Yay for that. And we're going to look at a short history. We'll have a fabrication overview. We'll have some video clips. But what better way to get started in a fun session with a fun video clip? And we're going to be listening to Stars and Stripes Forever, coming to you from Prince Albert Hall in London, England. So enjoy, and we'll be back in about 4 minutes. This is a short outline of what we'll be accomplishing today. We'll be looking at a short visual history, some of the key players, and I've just picked a few. Shockley, Bardeen, Grove, Fermi, and Dirac. We'll be having a little tiny biography of each of those, and then we'll have a section which I like to call On the Shoulders of Giants, and I've picked two from a rather large parameter space, but these are two of my favorites, Ludwig von Boltzmann and Leonhard Euler, and I hope when I'm finished they'll be your heroes too. And then we'll be looking a little bit of a fabrication overview, some video clips, specifically an ion implanter, take a peek inside a modern fabrication plant, and ending with a rousing rendition of the Brindisi from Verdi's La Traviata. So let's get started on a short history. This is a very short history, a visual introduction. This is a picture of the first device, and you'll notice that there is three areas that are delineated on the picture, and the emitter, collector, and somewhere here is the base, and all this part is the base here. It's made out of germanium. We'll have a little bit more to say about that. This is the world's first transistor, but it has characteristics of all transistors, even the most modern today. It has an in, it has an out, and it has a control grid which regulates how much comes out from how much comes in. The dimensions here, this is about a centimeter, so this is a pretty darn big device. And this is the same device in sort of a schematic, and here you see again the emitter, the input, the collector, the output, and the germanium base, which controls the whole deal. This is the significant part right here. Early transistors generally were made out of germanium rather than silicon. Both germanium and silicon form oxides according to the relatively simple chemical reaction here. This is a reaction which goes to completion. It doesn't go back. It's not an equilibrium reaction. The difference between germanium oxide and silicon oxide is that germanium dioxide, I should say dioxide rather than oxide, germanium dioxide is water soluble, where silicon dioxide, which is regular glass, is not. So the early transistors, well, you had to watch out because they eventually melted. And so the earlier radios that were made with silicon germanium or silicon substrates didn't last very long. So this is from chapter 1, and just a little bit of an explanation of what happens. These are the three main people that invented the transistor. They won the Nobel Prize, I believe, about 4 or 5 years later. This is Bill Shockley looking in the microscope, John Bardeen, and William Brayton. The first question that comes to my mind when I try to think of a caption for this picture is, why in heaven's name is he looking at a microscope? The thing is about 3 or 4 centimeters long, but I guess that's to impress people. The main person here is Bardeen, and we'll talk a little about him in just a little bit later. Shockley is pictured here a little bit later in life. Very, very interesting guy, to say the least. I claim here he's the most intriguing. Well, that's to put it mildly. He had the reputation as the world's worst manager. And because he was the world's worst manager, semiconductor industry benefited quite a bit because nobody could work with him, and everybody that worked with him quit and founded their own companies that competed against him. But I have to tell you, Shockley was a absolutely brilliant scientist, and he is responsible for some of the original work in acoustics, which I had worked on for many years, and trying to read his papers. The man's brilliance is absolutely incredible. But you can read about him in a book by Joel Shurkin called Broken Genius. He was definitely a genius, and he was definitely broken. He was a racist, he was a eugenicist, and he was a downright bad guy. And you can see some of his videos on YouTube, and perhaps form your own opinion. But I think the book is quite good in telling all about his life and about his philosophy. Of the three, this is my hero, John Bardeen. Bardeen is the only person to ever win 2 Nobel Prizes in physics. There have been a number of people that won 2 Nobel Prizes. Fred Sanger is one. Linus Pauling is another. Linus Pauling won a Nobel Prize in chemistry and in peace, which is kind of unique. Linus Pauling is a very, very interesting guy. Bardeen won his Nobel Prizes in physics for his invention of the transistor. He was a theoretician, and for his part in the BCS theory, Bardeen-Cooper-Streifer theory of superconductivity. He was a quiet, unassuming man, always a gentleman, and there's an excellent biography, which, again, the title captures, I think, his true essence, and it's called True Genius. And that's a really great title, The Life and Science of John Bardeen by Leonhard Euler. And I really recommend that because the man is a credible inspiration to all of us. A gentle, kind, and unassuming human being, besides being a true genius. Andy Grove was a refugee, fled to the United States from Hungary. They say he was a refugee both from Hungary and from Shockley. So he quit Shockley, formed his own company. I think we remember that name. It's called Intel. And here are the 3 founders of Intel. This is Andy Grove, Bob Noyce, and Gordon Moore. And who's that young kid? I think his name is Bill something. And this is with Andy Grove and a little bit later on. Andy Grove was not only a great manager, but a great physicist. He wrote one of the really great books in semiconductor devices. It's called Physics and Technology of Semiconductor Devices, and that's a book which is well worth studying. His autobiography is called Swimming Across, a memory, and is also quite interesting and worthwhile to read. Okay, moving right along, we're going to be studying quite detailed Fermi-Dirac statistics. So I picked both Fermi and Dirac. Fermi is one of the most amazing human beings that ever lived. His biography is called The Last Man Who Knew Everything by David Schwartz, and I think that characterizes Fermi in a very concise manner. He knew basically everything there was to know about science, both from an experimental point of view and as a theoretician. He had his feet in both pies, so to speak. He was a great theoretician. He won the Nobel Prize for his work on beta decay, and he was also a great experimentalist. He produced the first atomic pile in Chicago. I believe it was in 1942 or 1943. He was the theoretical head of Trinity. I didn't know that until I read his biography. Not of Trinity, in Los Alamos, excuse me. So he was head of the theoretical division in Los Alamos. He was present at Trinity. Trinity was the atomic bomb, first atomic bomb in July of 1945. And it was a plutonium device, which was quite complex compared to the uranium device, which was dropped on Hiroshima, and then Nagasaki was also a plutonium device. But anyway, he was in a bunker about 3 miles from ground zero, and he had on these dark glasses inside of this trench, and he, as the fireball strikes, this is an anecdote from the book, he holds up a piece of cardboard which has a crease in it, and he noticed how much the cardboard bends as the fireball was passing by, and by the angle of the bending he is able to do some quick calculations in his head. He didn't have a laptop computer, and he calculated the yield of the bomb accurately to within 10%. That's not trivial, and that just isn't gives you an idea of the brilliance of this guy. Paul Dirac. Well, I just finished his biography. It's called The Strangest Man, The Hidden Life of Paul Dirac, Mystic of the Atom by Graham Farmelo. Highly, highly recommended. Dirac was a fascinating, one of the most, again, brilliant theoreticians, not at all an experimentalist. He had nothing to do with experiment, but his mind was absolutely incredible. And he was a strange guy. Just a little bit of an anecdote about Dirac. He was giving a lecture in his later life. He ended his days at the University of Florida in Tallahassee. So he was giving a lecture, and somebody raised his hand in the middle of the lecture, and he said, "Professor Dirac, I don't understand that last equation." And Dirac continued to the lecture, ignoring the equation, and someone asked him after the lecture, "Professor Dirac, why didn't you answer the man's question?" And Dirac said, "Well, it wasn't a question, it was a comment." Typical Dirac, an amazing guy, and the book is wonderful. Read it, go out and read it, and if you can't get a hold of it, I have it online and I can email a copy to you. On the Shoulders of Giants. Again, I've picked out two giants. Let's look at them independently. Well, let's look first, Ludwig von Boltzmann, late 19th century, early 20th century. One of my heroes, and I don't know if I can convey my tremendous respect and affection for him in a few minutes, but let's just say he was the first man that believed in atoms. And this is his early picture, this is a later picture, this is the picture on his tombstone. Guess what that is? That's that's Boltzmann's constant. This is his most famous equation. The entropy is equal to Boltzmann constant times the log of the number of ways in which atoms or particles can be represented. He was despite his rather severe appearance, he was a kind, gentle person and a great teacher, and I hear he was even a very easy grader. The biography is called Ludwig Boltzmann, The Man Who Trusted Atoms by Carlo Sirigiani, and it's worth reading, although there is a fair amount of mathematics involved in it. So be aware that this one is going to be a little bit of a hard read, but the biographical information is very, very compelling. Ludwig von Boltzmann was found by I believe it was his daughter, Anna, in 1906, hanging from a chandelier. He was so despondent and so depressed that the world was not accepting his theories that he just could not go on in life. The person that took up the mantle of statistical mechanics, of which he was the founder, is a fellow by the name of Paul Ehrenfest, and in 1933, I believe it was, maybe 1934, Ehrenfest took a gun to his head and blew his brains out. What's the lesson of all this? Statistical mechanics is a very dangerous subject. It's one of my loves in my life, but it is not a trivial subject. So if you're going to study, and I hope you will study statistical mechanics, well, be aware and maybe listen to some Mozart while you're studying the subject. Okay, last but certainly not least is one of my all-time favorites and my superhero, Leonhard Euler, considered by many to be the most brilliant mind that ever lived. In his later years, he was blind. These are two pictures of him, probably a little bit earlier, maybe a little bit later. And he made incredible contributions that are still being deciphered to this day in number theory, complex analysis, calculus, trigonometry, and lots more. And he is best known for perhaps one of the most amazing statements ever written by man. It's called the God equation, and it links 1, 2, 3, 4, 5 entities which seemingly have absolutely no relationship to one another. Minus sign we learn in elementary school. 1 we probably learn in kindergarten. E is the ubiquitous Euler constant. Pi, the ratio of the circumference to the diameter of a circle. And I is this amazing number, the square root of -1. And people have been just amazed by this relationship. It doesn't make any sense, and that's why it's called the God equation. This is about as close to mysticism as we can come. Okay, so let's then move over to a short review of fabrication. This is an evolution from the year 2000 to the year 2020 of sizes of transistors. It starts at about 1300 angstroms, which is 130 nanometers, or 0.13 microns. That's a little over a tenth of a micron in size, beyond comprehension. Certainly, even in 2000, we could not see these devices using a light microscope. And now we're at about 100 atoms in length for a transistor. So there's about 1 billion or so transistors on a chip. Every one of them must be essentially perfect. If we have a process, for example, which has about 99% yield, or 99% of the devices are good and 1% is bad, the overall yield in a 100 process step will be something like 36%, and the wafer would be essentially worthless. 98% yield in a particular process, the yield, overall yield, would go down to something like 15%. So the yield per process must be essentially perfect. It is absolutely mind-boggling. Let's take a look at the different types of transistors. There are two main types. There are many branches of these types, but the two main types that we'll be talking about are the bipolar transistor. You see there is a go into, there's a go out of. The go in, or the input, is the emitter, the output is the collector, and the base is the control. The MOSFET comes in two varieties. I should say what MOSFET: metal oxide semiconductor. Say silicon, but we'll generalize it to semiconductor field effect transistors. The S just means it's plural, so we don't have to worry about that. One letter we don't have to worry about. Anyway, metal oxide semiconductor field effect transistor. There are two types. There are the NMOS, which has N type, donor type for the goes in and goes out, and then there's PMOS, which has acceptor type for the in and the out. Both cases have a control grid, which in this case is called the gate, and that controls the flow from in to out. Now, this is an overview of, a rather gross overview, I should say, of wafer fabrication. And I can just mention this is a personal aspect of this. I was responsible for the etch part, and for the ion implantation, mostly for etch. I was only responsible for ion implantation for a few months when we lost our ion implant engineer. Unlike photolithography, which is basically photography, and if you mess up on photolithography, you just do it again. If you mess up on etch, you throw the wafer away, or you throw the whole lot of wafers away, and that's true in ion implantation too. Extremely non-forgiving. So it's a relatively high stress job. You've got to get it. You've got to get it right. Okay. So I'd like to take a look a little bit at ion implanters, and then we'll take a look at a video of ion implanters. This is, I don't know who makes this thing, but this is the source over here, and the wafers are sitting about 10 feet away over here. So this is a pretty serious machine. These, what we call them tools, sell for anywhere from, I don't know, $2 or $3 million up. This one I guess I'm more familiar with because this is very nostalgic. It takes me back to my ion implant days. This is one of the machines one of the ion implanters that we had in our laboratory, and this is a variant, and the source is way back here next to the wall, and this is where you put your wafers. This has a rather nice feature. You can do what they call heated implants. So we would heat our wafers up to 600 or 700 degrees sometimes as we do the implant. This is all the controls, and I can tell you it was not simple to control this. Okay, so if we go back to the source, this is where we put the stuff that's going to be implanted. And I'd just like to take a look at two of the materials that we implant, phosphorus and arsenic. They're both donors. And phosphorus is pH 3, phosphine, and arsenic is in the form of arsine, arsenic trihydrogen. They're both gases. They're both horrible. Arsine probably being the worst of the two, but they're both bad enough. And what happens in the source is we create a vacuum, we apply voltage, we strip off the phosphorus, for example, as an ion, and then it is accelerated back down to the wafer, and then we put in an electron at the end, and the atom smashes into the silicon lattice. There's another interesting material called silane, which is silicon tetrahydrogen. This is generally a liquid at high pressure. However, if it leaks, it spontaneously combusts. And we had a silane fire in the fabrication plant where I worked, and we called the fire department, and they came. And they try to put out the fire with water, which is a no-no because water actually makes it worse. And to say the least, it was not a pleasant experience. Okay, let's look at a view of an ion implanter and a short video clip. So, ion implanter. The length is about, say, 12 to 15 feet. We're going to now turn around. And I'm going to hold the video when it gets to an interesting place. This is where we put the source. If it's phosphorus, it's a chemical species which contains phosphorus. And we strip off an electron, creating a phosphorus ion, which is accelerated through a series of electrodes until it gets to the wafers, which are sitting over here. The engineer or technician can enter into the ion implanter. This is a door. This is probably the most important part of the ion implanter. This is a shorting bar or a ground bar connected to ground. There are lethal voltages all over the place, even if it's powered down. So one has to be extremely careful. The wafers are sitting in this area right here, and the phosphorus ions, right before they hit the wafers, we replace the electrons so that phosphorus atoms are smashing into the silicon lattice. And now let's look at a view of peek inside of a modern silicon fabrication plant, and I think you'll find that one also quite interesting. Okay, this is a peek inside a modern fabrication plant. You'll notice the bunny suits covered from head to toe. Only the eyes are showing. These are the boxes of the wafers, and you'll notice they're extremely heavy, by the way. And you notice that everything is automated. This is an individual wafer coming into a tool. It's oriented. There's a little bit of a flat here which orients the wafer in a certain direction. This is the service aisle. Now, the people really don't have to wear their bunny suits. That's what they're called, bunny suits here. But it's a pain in the neck to robe and to disrobe and then to re-robe. So they keep them on. The air here is not nearly as pure. They're probably checking some of the vital signs of the tools. Notice how vast this is. I think this guy's getting lonely. I walk sometimes. I had a pedometer on. I would check my distance. Sometimes I walked as many as 6 miles in one day. So it's really quite remarkably large. This is inside. Okay. This is inside one of the tools. You get a feel for what's going on. In microscope, you can see the chips, but you can't see what's on the chips. It's far, far too small for a microscope, light microscope. Get an idea of the automation. This is a storage room where all of the individual wafer carriers are stored. Each carrier contains, I believe, 25 wafers, 10-inch, or sorry, 12-inch now. I think they're going to 16-inch. Every box is thousands and thousands of dollars, and you cannot afford to make a mistake. So it's quite a serious operation. These fabs run anywhere from, I think, $3 to $5 billion per fabrication. This is the robing room where people put on their suits. You can see the booties and the suits themselves. Every person has his individual suit with his name on it, and you can see how many of them there are. And finally, because this is a fun session, you'll notice there's no mathematics, which is great. Well, they want the God equation, but that's mystical. That's not mathematics. That's theology. So let's end with the Brindisi from Verdi's La Traviata, and we'll see you next time.